On May 31st, 2013, a tornado near Reno, Oklahoma, expanded to 2.5 miles wide, wider than Manhattan. Radar recorded winds approaching 300 miles per hour, deep into EF5 territory. Its official rating was EF3. But the contradictions did not stop at the numbers. High-speed radar captured rotation forming just 60 feet above the ground, not descending from the clouds the way textbooks said tornadoes are born. This was the storm that did not just break records, it broke the science. And to understand why, you have to start with what was silently building in Oklahoma's atmosphere that afternoon. Oklahoma's skies on May 31st, 2013, were loaded with invisible energy. Surface charts showed a classic collision. Warm, humid air from the Gulf pressed northward, while a cold front and a sharp, dry line advanced from the west. The intersection, known as the Triple Point, hovered just west of Reno. At this crossroads, the atmosphere stacked its cards for disaster. Radiosonde balloons launched that morning recorded convective available potential energy, CAPE, between 4,500 and 6,000 joules per kilogram. For meteorologists, those numbers are alarming. CAPE, above 2,500, means storms can explode upward, and here the values more than doubled that threshold. But the energy alone was not enough. A warm cap, a layer of air a few thousand feet above ground, acted like a lid on a boiling pot. It kept air parcels from rising, holding back the storm machine. All afternoon, the cap suppressed convection, letting instability build. Surface temperatures climbed near 35 degrees Celsius. Dew points hovered above 23, and the mixed layer depth reached nearly 2 kilometers. Every hour, the atmosphere became more primed, more volatile, while nothing broke through. The Triple Point's exact location mattered. High-resolution HRRR model fields showed the cold front surging southeast at 30 knots, the dry line retreating east at 20 knots, and a jet streak of over 140 knots aloft. Where these boundaries met, low-level winds converged, and streamwise vorticity, the spin in the wind, peaked. The ingredients for a supercell were not just present, but perfectly aligned. By late afternoon, the cap began to thin. Surface convergence intensified, and warm air advection from the low-level jet increased. Just after 4:10 p.m. local time, the cap finally gave way. The first updrafts punched through, tapping into the full reservoir of stored energy. Within minutes, radar would capture a tower of air shooting to 15 kilometers, the birth of the storm that would rewrite the science of tornadoes. But at this moment, the danger was still hidden, waiting for the trigger that would unleash it. 2 miles west of Reno, a white radar truck sat parked on the prairie, its dish spinning in a blur. Inside, Dr. Jana Hauser and Dr. Howard Bluestein monitored the RX pulse system, a mobile X-band radar capable of scanning the lowest layers of a tornado every 2 seconds. Most weather radars take minutes to complete a volume scan, but our AXPAL delivered a new snapshot before a human heart could beat twice. At 4:33 in the afternoon, as the first storm updrafts broke through the cap, RAXPOL's velocity fields began to show something unexpected. Not a descending vortex from the clouds, but a tight column of cyclonic winds spinning at ankle height, just 20 meters above the ground. In the data, this rotation intensified rapidly, forming a coherent, high vorticity core, while the air above remained relatively undisturbed. For 12 seconds, the low-level winds ramped up, reaching speeds usually seen only in established tornadoes. Only then did rotation become apparent higher up. Time series from the 2-second scans revealed a clear sequence. Surface winds converged and began to spin long before any visible funnel appeared. The radar's fine resolution caught a narrow ring of convergence, less than a city block wide, with vorticity values rivaling those in mature tornadoes. This was not the classic top-down process described in meteorology textbooks. Here, the tornado's engine was igniting at ground level, invisible to the eye and undetectable to slower conventional radars. The implications were immediate and unsettling. If tornadic winds could reach deadly strength before any visible funnel or hook echo formed aloft, then warning systems relying on visual cues or standard radar intervals would always lag behind the danger. For chasers and residents alike, the threat was already at their feet, hidden by rain and darkness, while the sky above appeared deceptively calm. The RX poll evidence forced a new question. How many tornadoes have begun this way? Their first lethal winds swirling in the grass while the world watched the clouds. Hauser and Bluestein's findings reframed the science of tornado detection. The storm that day was not just building upward, it was erupting from the ground, rewriting the rules of how and where to look for the first signs of disaster. Within minutes of the cap breaking, the El Reno supercell began a transformation that defied expectations. Meteorologists tracking the storm watched as radar reflectivity values soared, signaling a vertical updraft that blasted skyward with astonishing speed. The updraft core climbed from the prairie to nearly 15 kilometers, almost to the edge of the stratosphere, in just 16 minutes. This was not a gradual build, it was a vertical explosion, fueled by more than 4,500 joules per kilogram of CAPE, the kind of energy reservoir that only appears in the most volatile outbreaks. Horizontal expansion was equally staggering. As the storm's rotation intensified, the tornado's circulation ballooned outward, quickly surpassing the size of anything previously recorded. At its peak, the tornado's width measured approximately 4.2 kilometers, more than 2.5 miles across. To grasp the scale, imagine the distance from the Hudson River to the East River in Manhattan, all swept by a single, continuous vortex. This was not a narrow funnel, but a sprawling wedge, its boundaries blurred by curtains of rain and hail. The tornado's true size remained hidden from view, cloaked in precipitation that made visual tracking nearly impossible. Inside this expanding envelope, radar scans revealed a dense core of upward-moving air, with vertical velocities exceeding 60 meters per second. Reflectivity signatures showed a towering column of water and debris, the storm's internal engine running at full tilt. The rain-wrapped structure concealed the tornado's edges, creating a deadly illusion of safety for anyone outside the main precipitation shield. Chasers and residents alike faced a threat that was both massive and invisible, its reach extending far beyond the narrow tracks of classic tornado lore. The storm's internal dynamics were now in play, setting the stage for a new kind of stealth and danger, where size, speed, and concealment combined to outpace both science and instinct. Inside the tornado's vast, rain-shrouded core, the air was anything but steady. Doppler on wheels, motion tracks revealed a hidden world of turbulence, a tangle of smaller vortices, each spinning at breakneck speed and weaving unpredictable paths within the parent circulation. On the southern edge, these subvortices raced forward at 270 to 290 kilometers per hour, speeds usually reserved for the most violent tornadoes on record. The radar traces looked less like orderly spirals and more like a spirograph gone wild, with loops, hooks, and sudden reversals. This was not the classic steady funnel of textbook diagrams. Instead, the tornado's inner structure resembled a chaotic ballet, with each subvortex carving its own erratic trail. The danger was compounded by the storm's deceptive appearance. Rain curtains masked the tornado's true boundaries, and the main vortex itself was not alone. Just southeast of the core, a satellite tornado spun in the opposite direction, a rare, clockwise anticyclonic companion. For nearly 15 minutes, two tornadoes, one cyclonic and one anticyclonic, danced side by side, their tracks overlapping in the southern fields. The presence of this satellite vortex, confirmed in both radar data and ground reports, added another layer of unpredictability. Its motion was as erratic as the main storm, sometimes looping back toward the parent, sometimes veering off on its own. This internal chaos made the tornado's path impossible to predict from the ground. A chase vehicle could be clear one moment and then engulfed by a subvortex the next, with no warning visible through the rain. The trochoidal, looping tracks, especially on the southern flank, meant that even those with experience and distance on their side were suddenly at risk. For scientists and chasers alike, the El Reno tornado shattered the illusion of a predictable, visible threat. The storm's true motion could only be seen in the high-frequency radar data, and by the time the danger was apparent, it was often too late to escape. Tim Samaras built his reputation on patience and precision. While others chased the thrill of the funnel, he chased the data, one steel probe at a time. His signature device, the turtle probe, was a squat, armored instrument designed to survive the heart of a tornado. Stainless steel, low profile, packed with sensors, it recorded pressure, wind speed, and temperature every fraction of a second. In 2003, a turtle probe captured a 100 millibar pressure drop inside a South Dakota F4 tornado, a reading that still stands as one of the deepest ever measured directly at ground level. Samaras's approach to storm chasing was methodical, almost surgical. He mapped out chase routes with military precision, never relying on luck or bravado. Each deployment was a calculated risk, guided by real-time radar, wind profiles, and his own hand-drawn maps. The goal was always the same: get the probe in the path, get out, and let the instruments do the rest. On May 31st, 2013, the Twistex team rolled out with two vehicles, one carrying the turtle probe, the other serving as a backup and camera platform. Every detail mattered, from the mounting bolts on the probe to the timing of its drop. The turtle's design was the product of years spent studying what winds could do to metal, glass, and flesh. It was built to be left behind, to endure forces that no human could survive, and to bring back a record of the storm's secrets. For Samaras, the science was personal. He believed that the only way to understand tornadoes was to meet them on their own terms, with tools that could withstand their fury. The data collected by his instruments shaped not just academic papers, but the very questions that researchers asked about tornado structure and intensity. In a field where seconds and inches can mean the difference between insight and tragedy, Samaras's resolve and his turtle probe stood for a kind of courage that favored knowledge over spectacle. On Reuter Road, the illusion of safety vanished in seconds. Tim Samaras radioed his team that there was no rain there. They were in a bad spot. The words hung in the static, a final warning before the tornado's true reach revealed itself. GPS logs later reconstructed the moment. The Twistex Chevrolet Cobalt, a 1.3-ton car, was swept up and hurled 800 meters across the fields. The vehicle rolled and tumbled, its steel frame twisted beyond recognition. Tim, his son Paul, and Carl Jung were killed instantly. Their instruments, designed to withstand the heart of the storm, were found battered but intact, recording the last fragments of data. Close by, a Weather Channel SUV was caught by another subvortex. The chase vehicle rolled roughly 200 meters, battered by winds that left the frame crumpled and the windshield shattered. Against the odds, the crew inside survived, crawling from the wreckage as the tornado roared past. The same storm caught Richard Henderson, an amateur chaser who paused to photograph what he thought was a distant funnel. He never saw the rain-wrapped vortex enveloping the road until it was too late. The El Reno tornado's outer circulation was invisible, hidden behind walls of rain. Its sudden expansion, driven by rapid-fire subvortices, outpaced even the most experienced chasers. The ground truth, measured in meters and seconds, was merciless. Warnings based on visible funnels arrived too late for those in its path. 8 people died in vehicles that day, each one overtaken not by what they could see, but by what science had not yet learned to warn against. Mobile Doppler radar captured something unprecedented inside the El Reno tornado: peak winds reaching between 476 and 503 kilometers per hour, speeds that place it squarely in the EF5 category. Yet the official record, issued by the National Weather Service, lists El Reno as an EF3. The reason lies not in what the radar saw, but in what the tornado actually struck. The enhanced Fujita scale, since its adoption in 2007, is rooted in observable damage to human-built structures. In the fields south of El Reno, the tornado's path swept mostly open land, flattening out buildings and tossing vehicles, but sparing the kind of well-anchored homes or schools that serve as benchmarks for the highest ratings. Survey teams documented collapsed barns, shredded utility poles, and scoured fields, signs of ferocious winds, but not the total structural obliteration required for an EF5 label. Dr. Josh Werman, whose Doppler on Wheels team recorded those record winds, has long argued that this approach ignores the true hazard. He has said, if a tornado throws 300 miles per hour winds across a wheat field, it's still a 300 miles per hour tornado. He added, the wind doesn't care if there's a house in the way or not. He points to the El Reno event as a warning. By tying ratings to damage alone, the scale can miss storms that, by sheer luck, avoid populated areas, but still produce catastrophic forces. The policy debate intensified after El Reno. Internal National Weather Service documents show how the initial EF5 rating, based on radar data, was later revised downward after damage surveys failed to find the kind of destruction seen in Moore, Joplin, or Greensburg. This controversy goes beyond academic debate. Building codes, emergency plans, and public perceptions all depend on how tornadoes are classified. If the strongest winds are only counted when they hit something, critical infrastructure may be designed for less than what nature can deliver. The El Reno tornado exposed a gap between what technology can now measure and what policy is willing to recognize. For scientists like Werman, the question remains, should the scale evolve as our ability to see inside the storm improves, or will it continue to rely on the luck of the draw, on whether a tornado's worst winds find something to destroy? The answer will shape warnings, engineering, and how communities understand the true danger of tornadoes. The debate over the EF scale after El Reno changed not just ratings, but our thinking about how best to protect lives. For scientists and public safety officials, the aftermath of El Reno demanded more than reflection. It called for action. In the months that followed, meteorological institutions began reassessing the entire warning process. The RXPOL data made one fact unavoidable: tornadoes can reach deadly strength at ground level before any visible funnel appears or standard radar can detect a threat. Relying on visual cues or slow radar sweeps is no longer enough. Experts now advocate for high-cadence radar systems, tools that can scan the lowest levels of a developing storm every few seconds, not every few minutes. This shift means adopting mobile radar units like RXPOL as a model for national warning networks, so that low-level rotation is caught at its earliest stage, not after disaster has already struck. Chaser culture also faced a reckoning. The tragedy on Reuter Road exposed the hidden risks of rain-wrapped, rapidly expanding tornadoes and the false sense of security that comes from watching the sky for classic funnels. New Chaser guidelines emerged, discouraging crowding near high-precipitation supercells and setting stricter minimum distances from the core of any large, rain-shrouded storm. The days of racing the edge of a wedge, guided only by what is visible, are over. Now, chase teams are urged to monitor real-time radar feeds, heed warnings about trochoidal motion, and treat any HP supercell as a potential blind threat. Engineering standards, too, are evolving. The EF rating controversy showed that wind speeds measured by radar can far exceed what is inferred from ground damage. As a result, building codes for schools, hospitals, and critical infrastructure are beginning to incorporate radar-derived wind estimates, not just historical damage. This means designing structures to withstand forces that may never have left a scar on the ground, but are no less real. The lessons of El Reno are clear. Early detection, rapid communication, and a culture of respect for the invisible dangers of tornadoes are now at the heart of warning science. The reforms sparked by this event aim to ensure that the next time the sky loads the dice, the odds are better for everyone on the ground. Science now knows a tornado can grow wider than Manhattan, hide in rain, and spin off deadly vortices before the classic funnel appears. Relying on what we see, or on outdated ratings, risks more lives. Every warning delayed by doubt is a warning too late. Tornadoes like El Reno rewrite the rules, so our science and our safety must keep pace. Stay vigilant. Your seconds matter.